One of the classic systems studied in introductory physics is the pendulum. But did you know that the physics behind its motion is some of the most important that has ever been discovered? Stick with me on this journey as we explore how this simple object is illustrative of almost all oscillating phenomena in the universe. Let's look more closely at the pendulum. It swings back and forth under the motion of gravity, so the only forces acting on the bob are the force due to gravity, or weight, and the tension in the string. Weight is given by W equals mg, where m is the mass of the bob and g is gravitational acceleration, and it always points directly downwards. Tension is a little bit more tricky, as it changes as the bob moves back and forth. In general, since the pendulum's string never stretches, we can say that the tension is exactly the force required to keep the string at a constant length over the course of the pendulum's path. It points along the string from the bob to the anchor point. Now, Newton's second law of motion states that the total force on the pendulum, F, is equal to ma, mass times acceleration, and we now know that the total force on the pendulum is given by the sum of the weight and the tension. This is of course an equation of vectors, but we can simplify it by breaking it down into components. Specifically, if we measure the distance of the pendulum from the vertical as the fraction of the circle of radius L that it's traced out, then the position of the pendulum is given by S equals 2 pi LF, where F is this fraction. If we measure the fraction as the angle theta that the pendulum makes with the vertical, and we measure theta in radians, then this formula simplifies to S equals L theta. This is known as the arc length. Now, just as the second derivative of position is acceleration, the second derivative of the arc length is the acceleration of the pendulum along the path. Since we know that the pendulum always stays on this circle of radius L, we know that the forces perpendicular to the path must always sum to zero. This means that we only care about the component of the weight that is parallel to the path of the pendulum, and we don't care about the tension at all since it's always perpendicular to the path. Doing a little trigonometry, we find that the component of weight along the path is mg times sine of theta, which then tells us that the acceleration of the pendulum is given by minus g sine theta, or g sine s over L. Unfortunately, we now have a differential equation which is impossible to solve. To get past this obstacle, we will invoke a physicist's favourite tool, a Taylor series. Taylor series allow us to approximate smooth functions by polynomials, which will make our equation much easier to solve. The first non-zero term of the Taylor series for sine of x is just x, so we can replace all occurrences of the sine function with just the argument. By doing this, we are assuming that the argument is small, i.e. the displacement of the pendulum is small compared to the length of the string. How small? Well, it depends on how much error you're willing to tolerate in the solution. A maximum angle of around 20 degrees gives an error of around 2% in the approximation, which is still pretty good. This is known as the small angle approximation, and it is one of the most useful tools in the physicist's toolbox. Using this approximation, we have that the acceleration of the pendulum is minus g over L times s. So, we now have that the formula for the pendulum's path is something which is, when differentiated twice, gives itself multiplied by a constant. The functions that fit the bill here are the trigonometric functions cos and sine. We can just choose one and add a phase constant phi to represent the initial angle of the pendulum. Don't worry about exactly how we got this solution, I'll go over it in another video. For now, all we need to know is that for small oscillations, the motion of the pendulum looks like this smoothly varying wave. The velocity can be found by differentiating the position, and we find that it has the same shape but appears shifted a quarter turn out of phase with the position. In physics, we call anything that moves like this simple harmonic motion, and as we'll come to see, it's one of the most important types of motion you can study. We can also analyse this system in terms of kinetic and potential energy. The kinetic energy of the pendulum is given by half mv squared, and the potential energy of the pendulum is given by minus mgh, where h is the height of the pendulum below the anchor point. Using some trigonometry, we can see that h is equal to L cos theta. If we're being consistent, then we should really use the small angle approximation for cosine as well. The Taylor series for cosine is equal to 1 minus a half x squared when expanded out to the first non-constant term. This means that for small angles, we can write the potential energy as a half mgl theta squared, or a half mg over l s squared, where we are ignoring the first constant term because the absolute value of energy doesn't matter, only changes in energy. Notice now that the force on the pendulum, which is equal to minus mg over l times s, is equal to minus the gradient of the potential energy. This is not a coincidence, and it actually follows from the mathematical definition of potential energy. We'll see how this fits in later. Now we're going to take a break from pendulums and look at the motion of a mass on a spring. I promise this is related and everything will start to come together soon. So, as the spring extends and contracts, it experiences a force that gets greater the further it is from its natural equilibrium point. As a first approximation, we might say that the force is proportional to the displacement from equilibrium. Thus we write F equals minus kx, where k is some constant that characterizes how stiff the spring is, and x is the displacement from equilibrium. This is known as Hooke's law. Invoking the laws of Newton again, we can say that the acceleration of the mass is equal to minus k over m times x, and wait a minute, this looks quite familiar. The differential equation for the mass on a spring is the same as the one for small oscillations of the pendulum, meaning the mass on the spring exhibits the same simple harmonic motion. Looking from the energy point of view again, the kinetic energy of the mass is a half mv squared just like before, and the potential energy is given by the elastic potential, a half kx squared. This is an equivalent statement of Hooke's law, since we saw before that we can get the force as minus the derivative of the potential energy. Let's now consider an object moving under the action of some complicated force that we don't understand or have a formula for. It has some potential energy function u that we can measure since force is minus the gradient of potential. Let's just draw it like this. Now, let's suppose that the object is located at a point where the gradient of u is flat, and so the force is equal to 0. We measure the object's displacement from this point as x. Then let's use the almighty powerful Taylor series again to expand about this point. The first term is constant, and so in this case we can throw it away since it will disappear when we differentiate to get the force. The second term is 0 since we're looking at a point where u is flat. That leaves only the third term and beyond. But wait! This looks remarkably similar to Hooke's law. In fact, this is literally where Hooke's law comes from. If we differentiate this expression for u, we get that the force is equal to some constant times x. So, if the displacement from this point is small, then we can truncate the Taylor series and the motion of the object is exactly the same as a mass on a spring or a pendulum, simple harmonic motion. This has really deep implications. It shows that any system with a stable equilibrium point gives rise to oscillations which have this very simple form. These systems can be anything from simple classical systems like a pendulum or a spring, to more complicated scenarios like vibrations on a string, waves in water, or tree branches in the wind, or even quantum oscillations which can be used to describe the motion of atoms in a crystal, for example. Maybe we'll explore some of these in another video. So, thanks for watching. As you may have noticed, this is my first video. I have no idea what I'm doing, but I had a lot of fun making it, and if I'm being honest, it made me appreciate simple harmonic motion a lot more. I made this video for Sum 3, which is a competition designed by Grant Sanderson of 3 Blue 1 Brown fame, to get more people making maths and science education content on the internet. And he talks about one of the purposes of the competition being to motivate people that are close to making something anyway, and that was definitely true in my case, so I have to thank him for that. I already have ideas for some other videos, but if you have any feedback or anything you'd like to see, please don't hesitate to leave a comment. I'll see you in the next one.